Hello everyone, welcome back to CMME Made Easy, and I hope you all are doing very well. Before we begin, let me remind my dear students that the contents of this channel are only to supplement your knowledge, not to replace the regular online and offline classes in your institution. So please attend your classes and do not miss them. Also, if you like our contents, please subscribe to our YouTube channel, like the videos and share these videos with your friends, with your batchmates, with your juniors. Also, if you are a teacher, then with your students. Please follow our Facebook page and the link will be given in the description. Today, we are going to talk about one of the most important concepts in biostatistics, which is normal distribution. The concept may be a little bit confusing and difficult to understand, but it is very important that we understand what is normal distribution, what are the characteristics of normal distribution, etc. Because in biostatistics we need to apply a lot of statistical tests, and in certain situations when a data set follow normal distribution, we can apply a certain set of tests. Whereas in certain situations when the distribution is not following normal distribution, we cannot use that kind of test. Rather, we have to use a different set of statistical test. So that is why it is important that we understand whether a data is following normal distribution or not, and also what is normal distribution. We shall start with something that we already discussed in our previous class, that is histogram. So it looks somewhat like bar diagram, but the difference is the bars are adjacent to each other and there is no spaces in between the successive bars. Now if we find the topmost part of each bar, and in the topmost part we find the midpoint. So this is the topmost part of the tallest bar here, this one, and this is the midpoint. So like this we can find the midpoint for each and every bar. After that, if we add these two consecutive midpoints with a straight line, and we do this for the whole histogram, we can have a shape like this. This is known as frequency polygon. Frequency polygon, poly means multiple and gon means angle. So we have many angles in this shape. Here is an angle, here is an angle, here is an angle, there is another angle here is one, like this. Now frequency polygon can be converted into frequency curve. Now if you notice the x-axis here, we have the months. So number of cases being reported in the month of January, February, March, April, etc. Now rather than mentioning the number of cases in each month, if we could somehow manage to get the number of cases on daily basis, in that case the class interval would be much narrow. Here the class interval is 1 month, so month of January, month of February, like this. But rather than the whole month, if we could take the class interval of 1 day or even 1 week, in that case the bar diagram, the histogram would look somewhat different. So how to convert a frequency polygon into frequency curve? For that we need to fulfill two criteria. Number one, the class interval should be narrow. So rather than month, we could take daily reporting of cases. Also, the observations should be taken from a large number of samples. So suppose we are talking about body weight. So in that case, we could take the body weight, say about 5,000 people. So that is a large number of sample. Also, the class intervals could be very narrow, like 2.5 kg as mentioned in this example. So 20 to 22.5 here, 22.5 to 225, like this. In such situation, this frequency polygon actually loses its angles and it becomes a smooth shape like this. So this is what is known as frequency curve. So and that is how we can convert a frequency polygon into frequency curve, fulfilling only two criteria. Number one, narrow class interval. Number two, large number of observations. Now the next question is, what is normal distribution? So when a frequency curve is drawn based on large number of observations and narrow class intervals, these 2 points you already discussed, we're likely to get a smooth, symmetrical, bell-shaped curve. So after taking observations from a huge number of subjects, if we draw a frequency curve and it looks like a smooth, symmetrical, bell-shaped curve, then we can assume that the observation follow normal distribution, also known as Gaussian distribution. So normal distribution is also known as Gaussian distribution, and in such case that particular frequency curve is known as normal curve. So let us look at some examples here. Variables like height, weight, blood pressure, blood sugar, serum cholesterol, bleeding time, intelligence quotient, etc. So any quantitative variable that can be measured in interval or ratio scale. If we take such observations, for example, say height or blood sugar, if we take blood sugar from a huge number of patients and prepare a histogram from that data, keeping the class interval very narrow, we are probably going to get a frequency curve that is smooth, symmetrical and bell-shaped. In that case, we can say that the blood sugar level in the sample or all the observations that we have taken follow normal distribution. Now we have to remember, when it is measured in a large population or large sample, it may or may not follow normal distribution. So yes, it is very likely that if we take the observation from a large number of sample, it is going to follow normal distribution. But we can also have some situations where it may not even follow normal distribution. We can apply certain statistical test whether to see whether a particular data is following normal distribution or not, and we shall learn that thing in our future videos. But for the timing, just remember that even if we take a lot of observations from a huge number of sample, it is likely that the variable will follow normal distribution, but there can be some situations when the variable may not even follow normal distribution. So that is a possibility. What are the characteristics of a normal curve? It should be continuous, bilaterally symmetrical, smooth and bell-shaped, mean, median and mode all should coincide, and the central part is convex and it has two inflections and the two lines never touch the baseline. So let us explain all these characteristics in this diagram. So this is what a normal curve should look like. We have the x-axis here denoting the variable, the continuous variable. In the y-axis we have the frequency. Alright, so this is a continuous curve. As you can see, this is continuous line and there is no discontinuation or disruption anywhere. This is smooth bell-shaped curve because it looks like a bell. This is bilaterally symmetrical. So if we draw a vertical line in the midpoint of the curve, then one side of the curve is exactly the same, or you can say the mirror image of the other side. So that is why this is bilaterally symmetrical. In the central part we have the convexity of the curve. This midline that we have drawn here, it is denoting the mean or the median or the mode. So if we take the observations of any particular variable from a huge number of subjects, that means we have a lot of numbers with us, digits with us, and then we calculate the mean value, the median value and the mode value, we will see if the distribution, or rather if the observations are following normal distribution, then the mean value, the median value and the mode value that we have calculated are all same. So mean, median and mode values are same in normal curve or normal distribution. These two lines on the either side, which are known as tails, they do not touch the baseline or the x-axis. These are known as asymptotic tail. So the tails of the curve never touches the axis as it is asymptotic to the x-axis, indicating that a variable can take on any theoretically possible value, although the probability of it is very less. So if the curve touches the x-axis touching x-axis mean on the y-axis the value is 0 or the frequency is 0. So for that value we can say the frequency is 0. That means no person have that particular value. But we assume that a variable theoretically has every possible value. So theoretically speaking, we should not be having any person who does not have that values. The frequency should never be 0. So that is why, again, theoretically speaking, these lines should never touch the x-axis. But in reality, all the variables that we deal with in medical science, they have a rational range of values, right? For example, if you're talking about body weight of a human being, it can be few hundred grams. For example, we are talking about a very low birth weight baby, so it can be few hundred, maybe 500 gram, 400 gram, like this. So also a very obese person can be say 150 kg, 200 kg, even more than that. But we will never come across any person who has body weight of 500, 1000, 2000 kg. So we can say this variable body weight has a rational range of values. So if we are considering a body weight of 100 kg, in that case the frequency will always be 0, because not a single person can have that absurd amount of body weight. It is beyond the rational range of values. So that is why all the normal curve that we can draw for the variables that we use in our medical sciences, there can be values for which the frequency is 0. So that is why in such cases the tails of the normal curve can touch the baseline. So it is possible. But theoretically speaking, let me repeat again, theoretically speaking, it should never touch the baseline. Now the shape of a normal curve is determined by the mean and standard deviation. So if we have a large number of values with us, we can calculate mean and also we can calculate the standard deviation that we learned in our previous video on measures of central tendency, measures of dispersion, etc. This mean value and the standard deviation value determines what a normal curve will look like. Generally, mean value determines the position of the normal curve, and the standard deviation determines the shape, or better to say the width of the normal curve. If the standard deviation is more, the normal curve will be wider. So let us look at figure 5a. Here we have three normal curve. A, which is the flattest and widest, B is intermediate in terms of height as well as width, and C, which is very narrow but also the tallest one. Okay, the central line denotes the mean value, or you can say mean or median or mode, whatever, but let us talk about mean only. Okay, because we are dealing with continuous variable and mean is the best measure of central tendency. So for all these three curves the central line is same. So you can say all these three distributions or three curves have the same mean value, but since they have different width, that means they also have different standard deviation. In the next example, these normal curves, they have the exact same shape. The width of each curve is exactly similar to the other two curves. So in this case we can say yes, their standard deviations are exactly same, but as you can see they are positioned in different places. So the first one is A curve, followed by B curve, followed by C curve. So that is why their mean values are also different. So mu1, mu2 and mu3. Probably mu3 is the maximum value, followed by mu2 and then mu1. So this is the minimum value. So as you can see, based on the mean value and standard deviation, the positioning of the normal curve as well as the shape of the normal curve, or you can say the width of the normal curve, can vary. What is the importance of mean, standard deviation and the area of a normal curve? This is another very important concept that should be clear. So we have taken an example. So let us assume the body weight in a large population follows normal distribution. So if we measure the body weight of a huge number of subjects and then prepare a histogram with very narrow class interval, and from that we draw a frequency polygon, then a frequency curve, it should give a smooth bell shaped curve that is bilaterally symmetrical, etc., etc. And in that case we can say that the body weight in that population is following normal distribution. All right. Now the mean body weight in the population is 65 kg and the standard deviation is 5 kg. We already know how to calculate mean value and how to calculate the standard deviation. So these informations are given. This is what the normal curve should look like. In the x-axis we have body weight in kilogram. The mean value 65, that is why this is in the centermost part of the normal curve. The area under the curve is shown in the sky blue color or blue color, you can say. All right. Next we have to find out particular values, that is mean plus minus 1 standard deviation, mean plus minus 2 standard deviation and mean plus minus 3 standard deviation. So let us find these values. Mean plus minus 1 standard deviation, mean is 65, plus minus 1 standard deviation is 5, so 5 on either side. So 65 plus minus 5, that is 60 to 70. Right. Similarly, mean plus minus 2 standard deviation is 65 plus minus 2 standard deviation. So 2 into standard deviation is 5, 2 into 5, that is 10. So 10 on either side of 65, so 55 to 75. Similarly, mean plus minus 3 standard deviation. So 3 standard deviation is 3 into 5, that is 15. So 15 on either side of the mean value, that is 65. So 50 to 80. So now we have a particular range, mean plus minus 1 SD, mean plus minus 2 SD and mean plus minus 3 SD. The first one, the mean plus minus 1 SD, that is 60 to 70 kg. So we have seen all the people under this curve. So this is the area under the curve. 60 to 70 kg is basically one standard deviation around the mean on either side of the mean. It is seen that 68.3% of the normal curve is covered by the area, that is mean plus minus SD. Or in other words, in simple words, we can say that 68.3% of this population have body weight in between 60 to 70 kg. So if this is 100%, because the whole area is 100%, then the area between 60 to 70 kg will be 68.3%. Okay, it cannot be 100% of course, because we are not including people who have body weight more than 70 kg or who have body weight less than 60 kg. We are only considering in between 60 to 70 kg, and this area is actually 68.3% of the whole normal curve area. So in simple word, we can say 68.3% of the people from which this sample was taken, they have body weight in between 60 to 70 kg. What about mean plus minus 2 standard deviation? Here the range is 55 to 75 kg, and this area is actually 95.4% of the normal curve. So now we can say 95.4% of the population has body weight in between 55 to 75 kg. That means mean value plus minus 2 SD on either side covers 95.4% of the whole area of the normal curve. Mean plus minus 3 SD, which is 50 to 80 kg. Of course, now we are taking a huge range of body weight, right? So that means we will also include a huge number of people, most number of people in the given sample. That is actually 99.7%. So this area covers 99.7% of the area under the whole normal curve. In simple word, 99.7% of the population has body weight in between 50 to 80 kg. So as you can see, when we have narrow range, of course we are going to have less number of people within this range of body weight. When we are increasing the range, that means we are including more number of people in this range. Similarly, when we have gone to the 3 standard deviation value on either side of the mean value, we are having almost 100%, not exactly 100%, but 99.7%. That means almost all the people are included in between the 50 and 80 kg body weight range. So just to summarize, this is important, these values are important, and you should understand the proportional area enclosed between mean and multiples of standard deviation. Multiples of standard deviation means 1 SD or 2 SD or 3 SD. If we want, we can even calculate 4 SD, 5 SD like this. That is possible. So mean plus minus 1 SD is 68.3% of the total area. So this is the normal curve, and this blue highlighted area is standard deviation plus to minus 1. So 1 plus minus 1 standard deviation on either side of the mean value covers 68, not exactly 68, but 68.3% of the total area. Similarly, 2 standard deviation on either side of the mean value covers 95.4% of the total area, and 3 standard deviation on either side of the mean value covers 99.7%. That means almost 100%, not exactly 100%, but almost 100% of the total area. Only few number of subjects will be beyond these values. So with this, I think the concept is a little bit clear right now. So when we take measurements from a huge number of subjects and then try to draw a frequency curve from that, if the frequency curve have few characteristics like it is smooth and bell shaped, bilaterally symmetrical, and mean median mode all coinciding, in that case we can say this frequency curve is actually a normal curve and the values or the observations are following normal distribution. And when we are talking about normal distribution, we should have the idea about the mean and the standard deviation and how they determine the amount or the area under the normal curve. So 1 standard deviation value on either side of the mean covers approximately 68.3% of the total area. 2 standard deviation on either side of the mean covers 95.4%, and 3 standard deviation on either side of the mean covers 99.7% of the total area, right? So with this, we conclude today's session on normal distribution. If you like the video, please subscribe to our channel and share this video with your batchmates, juniors and friends from other colleges. We also have our Facebook page that you can follow. The link is given in the description. Take care, and we shall see you in our next video.